Good morning from Washington, D.C. Today I want to go over what's called a bifurcation. So, a bifurcation was first coined by Henri Poincaré, who's a famous name in the field of dynamical systems. And it really refers to what it refers to is a dynamical system where you have a parameter or maybe more than one parameter in the dynamical system and you have different behavior. It's the point where that dynamical behavior changes. So we recall the logistic equation that we had before. We've already looked at this. This program is already inside your Dropbox. Um, I'm going to remind you here that we set up a scroll bar to scroll the values of R, and the dynamics here, we would say the dynamics are that it converges to the equilibrium value, the second equilibrium value. In this case, this particular still, it's at 0.29972. Now let's keep scrolling, and then we will start to see a change in behavior. We start to see some wiggling here at the beginning, but it's still converging. Long-term behavior stays the same. Start to see more wiggling. And right at between 2.996, you still see oscillation but convergence to the equilibrium value. But then at 3.028, I see a periodic point. And I can even look over here and say that my periodic point it's bouncing, it's a period 2 point. Looks like it if I keep going down. So far. All right, so let's take a look at a different map and start changing this thing and looking at bifurcation, a different bifurcation problem. So we would call, in this case, R equals 3 a bifurcation. Before we go to a different one, I changed my mind. Let me go to and show you another bifurcation. So here we have period 2 points, and it looks like we have something else here. It's possible that we have now a period 3 point. Looks like we have a period 3 point, or maybe even period 4. So here around 3.4, we have another bifurcation. And now clearly when I just jumped over 3.54 looked nice and ordinary, but 3.57 looked, we have chaos. So around 3.57, 3.6, we have another bifurcation. Okay, so this is a pretty complicated map. Let's take something easier. Push this forward here. The map I want to iterate this time is r sine of x. So I can actually go into my code and change it. So I'm going to go in here and change it. And I want to examine whether r equals 1 is a bifurcation point. So that means my scroll bar has to include r equals 1. So I could probably just go modify this because if you recall, I set up the counter. Let's go back to the counter. We might have to do some changing around here. But if you recall, we had the counter go from 0 to 4. Let's see how far it goes. Yeah, 0 to 4. 3.7 there. So I must have made some decision in class where we did this before that it's going to go from 0 to 3.7. But if I want to examine right around 1, maybe I would like to have this not go from 0 to 3.7, I would like it to go from maybe 0 to 2. So it surrounds 1, but it's a little smaller window. Recall how we did that. The numbers inside the scroll bar go from 0 to 100. So the minimum value is equal to 0. The maximum value is equal to 1. Nice undo button here. Okay, so maximum value is 100. This is why we use LaTeX. Okay, so now I want, instead of the minimum value going from 0 to 100, I would like the minimum value but I want the maximum to be 2. So how we did that is we set up a line, a linear transformation. We have y equals mx plus b. And I know that the minimum should be 0. So when x is 0 from the input of the scroll bar, my y value should be 0. So this implies that b is equal to 0. So now I have y equals mx. Now what I want is that at 100, which is the maximum value, I would like my new max to be transferred to 2. So what I would like was 2 to be my new output when the input was 100. So this tells me that my m is 2 divided by 100. Or if you want to get fancy, it's 1 divided by 50. Okay, so now I have my transformation. My transformation is y equals 1 divided by 50 times x. So I go into here and into my other counter, and I just change it. There's the counter goes from 0 to 100. That's where the scroll bar's hooked. And I'm going to change this to 1 over 50 times the x value, which is in cell D2. So now I can see it's at max value. So it's now doing what it's supposed to do. It's starting out at 0, see the R, and then it's ending up at and I'm going to erase these equilibrium values because we're not going to be using them right now. We don't need to see that. And I'm going to change my function to the function that I want to use. This time I'm changing my function. I talked to the plebes quite a bit about how important it was to comment and be neat in your anything you code because you will forget. So I actually could pull this up from my MA 103 class because I'd written it out so nice. I knew exactly what was going on. So good habits for programming are important. So I'm going to put this here. We have a different function. I'm going to save this as r sine x. So I know what it is. Okay, so now I'm going to change this function that I'm iterating. It's going to be $2 stays the same, so I'm going to modify that, and then we'll put sine of x in this case would be a2, or the previous iterate b2, because we're taking the previous seed and running it through, and then we need to scroll this down. Jake, I'm sure, has already figured out a way to fill that. I'm doing old school here. And we see now a new dynamic behavior in this new function. I still have the same graph set up here. And I can scroll my R. So let's see what happens. If R is 0, does that make sense? Yeah, if R is 0, I should just flat out drop to 0. And then I'm going to start scrolling. It looks like it's converging to 0 no matter what happens here. And then I see it starting to lift off. And right at 1, it's not converging to 0 anymore. It looks like it might be converging to something else. So now I get non-zero, right at r equals 1, it seems like I get something else other than 0 as being the value. Now let's change the initial condition a little bit and see if that still holds. Let me change it to 0.2. Doesn't seem to do much. 20. Oh, that's interesting. If I change the initial, well, that might be my axes. Let's go look down here. Maybe we should actually scroll this down further, right? So let's do that. Let's make it go to about 1,000 iterates. And it definitely looks like it's converging. It's not, and not to 0. So it still converges to a non-zero equilibrium. So let's graph that. So I'm going to highlight these two, insert, scatter. This is the old version, by the way, and I don't like that format, so I'm going to change it to this. And XN. And I hate these lines. They look ugly. That's gone. So I still see convergence, but I've lost kind of, because it's so big now, I've lost the fact that it's not, it looks like it's converting to 0, but I can look at the data and see that it's not. So let's take a look at the data. Here definitely it's converging to 0. So right before 1, it's converging to 0. Right after 1, it's converging to a non-zero equilibrium value. So I would characterize this as I wonder why. So the first thing I'd like you to do is to look at the equilibrium values. So take a minute out now to look at the solution to this at r equals 1, and also look at when r is less than 1. Find the fixed points first. So what you can do is you can write down your fixed points and send it to me as a text, your work. Just take a picture of your work and send me a text. So I have that. Or you can type up your work and send it to me as like I'm typing it into a file. You can use LaTeX, you can use Word, and send it to me, and I should get it within half an hour after the class is over. So go for it, try it out.